Good day, Ms. Cañete. We are the Group 10, and today we will be presenting to you our analysis of the study entitled Assessing the Influence of Hydraulic Boundary Conditions on Clay Slope Stability, the Fontana Monte case study. So, I will be the one presenting the introduction and case study overview. First of all is the background of the Fontana Monte case study. So the Fontana Monte case study focuses on a large, slow-moving, and deep-seated landslide located on the northwestern slope of Volturino in southern Italy. The slope is primarily composed of highly plastic, fissured clay belonging to the Topo Capuana or TPC formation and is underlain by calcareous rock layers containing a groundwater aquifer. Historical investigations revealed that the landslide has existed since at least the 19th century and continues to experience seasonal reactivations up to the present time. Evidence of slope movement has been observed through damage to roads and nearby structures, as well as through long-term inclinometer and piezometer monitoring data. So next is the objectives and significance of the study. Next, please. So the primary objective of the investigation was to determine how hydraulic boundary conditions affect the piezometric regime and overall stability of the Fontana Monte slope. The researchers specifically aimed to analyze the influence of rainfall infiltration, evapotranspiration, groundwater recharge, and seasonal groundwater fluctuations on landslide activity. Another important objective was to evaluate the effects of slope vegetation atmosphere or SLVA interaction on deep clay landslides. The study sought to understand how climatic conditions, vegetation processes, groundwater groundwater flow interact to influence seasonal changes in pore water pressure and slope movement. So next is next is the overview of the methods and approach used in the study. So the study used a combination of geological, hydrogeological, and geotechnical and numerical investigation methods to evaluate of the Fontana Monte slope. Geological and geomorphological investigations were first conducted to identify the soil and rock elements, landslide geometry, and existing slip surfaces in the study area. Field monitoring meters were installed to measure groundwater pressure, landslide displacement, and determine the depth of movement. Long-term monitoring data allowed the researchers to observe seasonal fluctuations in groundwater pressure and landslide activity. Laboratory testing was also performed to determine the hydraulic and mechanical properties of the clay soils, including permeability, compressibility, and shear strength. These properties were necessary for evaluating the behavior of the slope under changing groundwater conditions. That's all for the introduction and case study overview.
So, I will now proceed with the analysis and discussion of the study. So, 2.1 Hydraulic Boundary Conditions in Slope Stability. So, hydraulic boundary conditions refer to the factors that control how groundwater flows, is stored, and moves within slope materials. So, these conditions are very important in slope stability analysis because they directly influence pore water pressure, which is one of the main factors controlling soil strength and overall slope stability. So, in general, these conditions are governed by rainfall infiltration, evapotranspiration, and aquifer recharge. These processes act as the main water inputs and outputs in a slope system, determining how much water enters, leaves, or remains stored within the soil layers over time. In the Fontana Monte case study, a calcareous aquifer was identified beneath the slope. So, these aquifer continuously supplies water to the overlying clay layers, resulting in consistently high groundwater levels, even during non rainy periods. This makes the slope more sensitive to seasonal changes. So when groundwater levels rise, pore water pressure also increases. The influence of water on clay slope stability. So water has a major influence on slope stability because clay soils are highly sensitive to even small changes in moisture content due to their low permeability and fine particle structure. So when water infiltrates into the ground, it fills the pore spaces between soil particles, leading to an increase in pore water pressure. This process reduces the contact force between particles, which weakens the internal structure of the soil mass. So as pore water pressure increases, effective stress and shear strength decrease significantly. This makes the slope less resistant to gravitational forces and increases the likelihood of slope movement or failure. During intense or prolonged rainfall events, the soil can become fully saturated. Saturation increases the weight of the slope while simultaneously reducing its shear strength, making it highly unstable. Shallow groundwater systems respond quickly to rainfall because they are directly influenced by surface conditions. In contrast, deep groundwater systems are controlled by aquifer recharge, which changes more slowly and influences long term slope behavior rather than immediate responses. Due to these combined effects, water is considered one of the most dominant and continuous triggering factors of landslides in clay dominated slopes. Next is we have the 2.3 methods used to evaluate slope stability. So to evaluate slope stability in the Fontana Monte case study, the researchers used an integrated approach combining geological, geotechnical, and numerical methods to ensure a complete understanding of slope behavior. So, geological and geomorphological mapping was first conducted to identify the surface structure of the slope, including lithology, geomorphology, and the boundaries of existing landslide zones. This step helped define the spatial extent and characteristics of slope deformation. Borehole drilling was then carried out to obtain detailed subsurface information. This allowed researchers to identify soil layers, depth of clay formations, and groundwater conditions below the surface. So, piezometers were installed at different depths to measure pore water pressure and monitor groundwater variations over time. These measurements were essential in understanding how water pressure changes affect slope stability. We also have here inclinometers. They were used to monitor slope, displacement, and detect internal ground movement, helping to identify active sliding zones and movement rates. Laboratory testing was also performed on collected soil samples to determine key geotechnical properties such as permeability, compressibility, and shear strength. These properties are essential inputs for stability analysis. Finally, numerical modeling was also used to simulate slope behavior under different conditions. We have here the finite element method, which was applied for seepage analysis to understand groundwater flow patterns, while the limit equilibrium method was used to calculate the factor of safety, which indicates the stability condition of the slope under varying groundwater scenarios. Next, we have 2.4, the conditions that increase slope failure. So there are several environmental, geological, and mechanical factors that contributes to slope failure in the Fontana Monte area, often acting together rather than individually. So heavy rainfall and prolonged wet periods significantly increase water infiltration into the soil. leading to saturation and progressive weakening of slope materials over time. High pore water pressure caused by continuous groundwater recharge reduces effective stress within the soil, decreasing its ability to resist movement. Clay soils naturally have a low permeability, meaning water drains very slowly. This causes water to accumulate within the slope, increasing saturation levels and instability. Additionally, clay soils have inherently low shear strength compared to other soil types, making them more vulnerable to deformation and failure under stress. Seasonal seasonal fluctuations in groundwater further worsen stability conditions because repeated cycles of wetting and drying gradually weaken soil structure. Other external triggering factors also can contribute to slope failure. Seismic activity can disturb the internal structure of the slope. External loading adds additional stress that the soil must support, and temperature changes can influence moisture conditions and soil behavior over time. Next, we have 2.5 mitigation measures for clay slope stability. So, to reduce the risk of slope failure, the study emphasizes that groundwater control is the most effective and critical mitigation measure. Subsurface drainage systems, drain trenches, and horizontal drains are commonly used to reduce excess pore water pressure. By removing water from the slope, these systems help restore effective stress and improve soil strength. Monitoring systems such as isometers and inclinometers are also essential because they provide continuous data on groundwater conditions and slope movement. These systems allow engineers to detect early warning signs of instability before failure occurs. Engineering based slope protection measures such as regrading, retaining structures, and toe protection help physically stabilize the slope by reducing driving forces and increasing resisting forces. Vegetation management also contributes to stability by reducing surface runoff, minimizing rainfall infiltration, and increasing evapotranspiration, which helps remove excess water from the soil. Surface drainage systems are also important because they prevent water accumulation at the surface, reduce erosion, and limit additional water infiltration into deeper soil layers. Next, we have the 2.6 critical analysis and course relevance concepts. So this study is highly relevant to engineering, no? To engineering geology and geotechnical engineering because it clearly demonstrates how groundwater behavior controls slope stability. It applies several fundamental geotechnical concepts, including pore water pressure, permeability, seepage analysis, and factor of safety. These concepts are essential in understanding how slopes behave under different environmental conditions. The study also integrates multiple methods, which is the field investigations, laboratory testing, and numerical modeling, which strengthens the reliability and accuracy of its findings. One of the most important insights from the study is that rainfall alone is not sufficient to trigger landslides. Instead, deep groundwater recharge from the underlying aquifer plays a major role in maintaining high pore water pressures that contribute to long term slope instability. Overall, the study is highly valuable for disaster risk reduction as it improves understanding of landslides. As it improves understanding of landslide mechanisms and supports better prediction and mitigation strategies. Lastly, we have the 2.7, the strengths, limitations, and implications of the study. So the study has several strengths, particularly its comprehensive and multi-method approach. By combining fieldwork, laboratory testing, and numerical modeling, the researchers were able to develop a more complete and reliable understanding of slope behavior. Another strength is its strong focus on groundwater dynamics and seasonal variations, which are often key factors in deep seated landslides but are not always fully analyzed in other studies. However, the study has also limitations. So there are uncertainties in soil properties and groundwater measurements, which can affect the precision of the results. So in addition, numerical models rely on assumptions about soil behavior and boundary conditions, which may not perfectly represent real-world conditions. Despite these limitations, the study also has strong practical implications. It is highly useful for engineering design, particularly in assessing and stabilizing deep seated landslides. It also contributes to improving landslide prediction models and developing more effective mitigation strategies for hazard prone areas. That is all for my part.
Let's now proceed with the insights and recommendations of the group. First, next slide, please. First, the group insights and realizations. On the deep ground water being the main driver, one thing that really stood out to us is that it's not just the rain at the surface causing the landslide to move. The big trigger is actually the deep aquifer beneath. Even when the top layer looks fine, that if the deep water pressure builds up, the slope starts to creep. That change how we think about clay slopes. You can't ignore what's going on underground. On the timing of movement, we also notice that the movement isn't random. The slope only speeds up in the late winter and spring. That lines up exactly with the when the aquifer recharges and water pressure peaks. So it's basically following the seasonal water cycle. Once we saw that, we made it the whole thing. We made it made the whole thing make sense. Next slide, please. Next, on monitoring the deep, shallow layers. Another realization was how important it is to monitor both deep and shallow points. The piezometric heads at 25 meters and 50 meters were moving together. That told us that the aquifer and the landslide are connected. If we'd only checked the shallow sensors, we would have missed the whole story. And then on the small changes in factor of safety, we realized that even a tiny drop in the factor of safety matters. It only went from 1.08 down to about 1.0, but that was enough for the slope to start moving faster. So the marginally stable really does mean that you need to keep an eye on it. Then we have the recommendations and possible movements. Next slide, please. First, on testing mitigation measures, if we take it this further, the first thing that would suggest is that actually testing the test solutions. The study shows that the aquifer is the problem, but it doesn't look at what you can actually do about it. So running models with deep drains and depressurization would make it a lot more useful for engineers on the ground. On using coupled 3D modeling, right now the model is 2D and uncoupled, meaning the water flow and soil movement are done separately. In reality, those two things actually affect each other. So, moving to a coupled 3D model would give a more realistic picture, especially for more complex sites. Next slide, please. Then, on adding climate change scenarios. The study only uses data up to 2021, but the climate is changing. So rainfall and recharge patterns might shift. If we run the model with future climate scenarios, we'd get a better idea of whether the slope actually gets riskier over time. And then we have expand expanding on other sites. This was just one site. The geological factors here is pretty specific. Fissured clay over a karst aquifer. To make the findings more general, it would help to test a similar slope, whereas if we see the same aquifer driven behavior shows up. On improving early warning systems for practical use, the big recommendation is to include deep underground monitoring in early warning systems. Right now, the most systems just track rainfall and shallow soil moisture. If you're not measuring deep aquifer, you might miss the real warning signs. Now let's proceed with the conclusion.
Okay, so for now, the conclusion okay, next slide. For section 4.1, the summary of the discussion. Our summary of findings focuses on the examination of the hydraulic boundary conditions to determine the effects of groundwater movement, rainwater infiltration, and poor water pressure on landslide occurrence. This our summary of findings focuses on these types of kanang landslide occurrence by combining field methods like borehole drilling, piezometers and inclinometers with laboratory tests and numerical modeling. This research tracks how water alters the properties of lake soils. Next slide. So for the slope instability, it is driven by two distinct sources. The shallow and deep ground water flow. When seasonal rainfall and deep aquifer recharge peak, they cause a significant spike in pore water pressure. This directly reduces the effective stress and degrades the shear strength along the soil spell planes. So this proves also that relying solely on surface precipitation indexes will cause engineers to fundamentally miscalculate the safety factors of deep clay slopes. To mitigate the landslide risk effectively, we must move towards the comprehensive engineering solutions that actively manages the deep groundwater, maintaining long-term monitoring systems, and implement structural stabilization. Now for the 4.2, or the takeaways and the lessons. So first is, do not solely rely on surface maps. So since for deep-seated slides, monitoring surface metrics like rainfall depths alone is highly misleading and directly causes dangerous factor of safety miscalculations. The real failure is hidden deep underground. So because of this, validating our data is an absolute necessity. To get an accurate, reliable assessment, we cannot look at data sets in isolation. We must combine and cross validate using laboratory testing or the control parameter on-site instrumentation to capture the real-world tracking and computer modeling to cross-validate. Now, let us answer the five questions given to us that is about our case study. So first is, what are hydraulic boundary conditions in slope stability analysis? Hydraulic boundary conditions define how water enters, exits, and exerts pressure on a soil mass at its boundaries. They include surface boundaries like rainfall infiltration and vegetation evaporation, alongside subsurface boundaries like the groundwater flow. In this case study, these boundaries dictate how a highly permeable deep rocky aquifer interacts with a neighboring clay slope to control the subsurface fluid pressure over time. Now, next question. Next slide. Number two is, how does water influence the stability of clay slopes? So water destabilizes clay by altering the internal stress states and degrading the soil's mechanical resistance. So as water fills the pore spaces, pore water pressure rises, which directly reduces the effective normal stress holding the soil framework together. Because a soil's operational shear strength depends entirely on this effective stress. The rising fluid pressure strips away the structural resistance along failure plains. And this triggers the landslide movement. Now, number three, next slide, please. So, number three, what methods were used in the study to evaluate slope stability? So, the study evaluates slope stability using an integrated pipeline of field monitoring, like the applied methods that I discussed, the geological mapping, the borehole drilling, the piezometer monitoring, and the inclometers. So these empirical field datasets were then cross-validated through controlled laboratory shear tests and simulated using 2D elements. Now, number four, what conditions increase the likelihood of slope failure? So so failure likelihood increases when a highly permeable aquifer sits next to a low permeability clay, creating a hydraulic pump effect that sustains high water pressure at great depths. Under these intense baseline conditions, the clay matrix becomes hypersensitive, meaning even a tiny variation in deep groundwater levels can severely degrade the soil shear strength. Furthermore, the risk of failure increases when the analysis relies slowly on surface rainfall maps, as this completely misses the deep-seated pressure anomalies. Now, for the last question, number five, what mitigation measures can improve the stability of the clay slopes? So this actively so th- so first is the combining deep hydraulic drainage and surface water management and structural reinforcements. Next is the installing of perforated subhorizontal drainage borings into the upstream aquifer. This actively relieves the deep pore water pressure before they can ever reach and weaken the clay matrix. By pairing this deep drainage with surface ditches and concrete piles, we successfully anchor the slope and eliminate the primary triggers of failure. Now that is all for our case study, and I hope you have listened well. That is all. Thank you.